So in today's lecture, we will do the time response analysis of the first order system. Okay. So if you talk about the practical first order systems, so that is like RC, RL circuits, like a low pass filter, high pass filters. So if we talk about the practical first order system, so that is like RC and RL circuits. Okay. So now here you can see the open loop system, which is connected in with negative feedback. Okay, so this overall system is a closed loop system, closed loop negative feedback system. So order of this system is 1 because there is only one pole in the system, open loop system. And what is the type of system? What is the type of this system? Anyone? What is the type of this system? Anyone can reply.
First order.
No, order is first only, but there is a type also, no?
We define type for open loop system na.
So what is the open loop transfer function here? No. Uh, when we find out the type using open loop transfer function, okay? So here you can see a block diagram. What is the open loop transfer function here? Even if the closed loop system is given, that system, huh? Okay, even if the closed loop system is given, that closed loop system consists of one open loop system, right? By using one open loop system with the feedback, we construct the closed loop system, right? Okay, so every system, open loop system has a type and order. So what is a type and order for this particular open loop system? This is, so I'm talking about this one, right? So what is the open loop transfer function here? Yesterday we have seen, na?
1 upon s into tau.
Yes, right only. So open loop transfer function is G of s into H of s, right? So what is H of s here? Unity gain feedback we have used, right? So that is one only. So open loop transfer function will be G of s. And so what is open loop transfer function here? 1 upon s into tau. So what is the type here?
1.
Type is 1. Because number of poles present at origin is 1, right? And number of poles in S domain is 1 only. Okay. So can anyone tell me what is the Laplace transform of impulse response of any system? We have seen this when we have seen the LTI system. What is the Laplace transform of impulse response of any system?
1.
No.
1.
Laplace. Okay, the difference between this particular response and signal. Okay, if I talk about impulse signal, that will be this one, this signal, right? So Laplace transform of this is 1 only. But what about impulse response? What is mean by impulse response? We have seen now. So this is a control system, right? Now for this control system, if I say for this LTI system, H of S is its transfer function of that system, okay? So if X of t is the input and Y of t is the output, right? So what is meant by impulse response? When I apply the impulse signal as an input to this system, whatever the output I am getting, it is called as the impulse response. Okay. When I apply the step signal to this system, whatever the output I will get, that output I will call as a step response. Okay. Now, as we know, this is a LTI system, right? So if we say the impulse response is h of t here, okay? The impulse response of this system is h of t. Okay, so what is the output y of t? Y of t is x of t convolved with h of t because this is a LTI system. So if we convert this equation into Laplace domain, what is the resultant equation? Y of s is equal to x of s into h of s, right? Okay. So what is x of s when you apply del of t? What is the x of s when you apply del of t? 1. Laplace transform of del of t is 1. So y of s is h of s. Okay. So when you apply the impulse signal as an input to the LTI system, at the output side you get impulse response of the system. Okay, means whatever the system, for example, if this is a RC filter, right? So in this R and C are the components. Okay, so this impulse response shows this component nature. Okay, it doesn't have don't have any effect of any input on this particular system. It just represents the system, RC system. Okay, if you consider this particular system. So when we apply the impulse signal to our system, at the output side we get the impulse response of the system which describes the system. Okay, so now if I got this h of s, if I take a ILT of this, so I will get h of t, right? Now if I got this h of t, now for any input, if I apply the step input, okay, for any input I will be able to calculate my output. So y of t will be u of t convolution with h of t, right? Similarly, if you apply ramp signal, then also you can calculate the output. So have you understood? When you apply the impulse signal at the input of any LTI system, at the output you get impulse response of that system. Okay, we generally represent this system. Have you understood? Yes or no? Or should I explain it again?
Yes, sir.
Okay. So first, for this particular system, we need to find out the impulse response of the system. Now to find out the impulse response of the system, first we need to find out the transfer function of the system. So h of s is what? Transfer function of the system. Okay. So h of s is transfer function of the system. So if I take this, have you understood this point? If any doubt is there, you can ask me, because if you don't reply, I will not. Are you getting this point? Okay, ठीक. So yes. Okay, ठीक है then. Now you consider this system and find out the transfer function of this system. C of S upon R of S. Now you tell me what is the transfer function of this system? Anyone?
One upon one plus 1 by S delta.
S tau into 1. Okay. The forward path gain divided by 1 plus G of S into H of S. H of S is 1, right? So this is G of S upon 1 plus G of S into H of S, because there is a negative feedback, right? Okay. So if I simplify this, okay. So this is what C of S upon R of S. So this is a closed loop transfer function, right? So this is a closed loop transfer function. Now, impulse response means when we apply the input signal as a impulse signal. Okay. So R of t will be, so in this case, R of t will be delta of t, and Laplace transform of that will be 1, right? So Laplace transform of that is 1. So in this equation, so this will be R of S, right? So here I apply that
Sir, the
signal. So
screen
R
is
of S.
freezed. Excuse me.
Now,
Sir, it's freezed.
okay. I think there is a network issue. Now it's visible properly.
Yes, sir, yes.
Okay, now I put R of S is equal to 1. So C of S will be 1 upon tau, 1 upon S plus 1 upon tau. Okay, so this will be the C of S. So this is the impulse response of the system. Okay, so if I make some space here. Now, if you take a inverse Laplace transform here, what will be the inverse Laplace transform of C of S? C of t will be. So, what will be the inverse Laplace transform of this particular response? What is the inverse Laplace transform of this particular response? One upon tau e raised to minus t by tau u of t, right? So this is the impulse response. Okay. So if I draw this,
Excuse me, sir. Why
yes.
did you take that R of S as 1?
Because here R of t is delta of t, na? So Laplace transform of delta of t is equal to 1. That is R of S. That is a Laplace transform of R of t. Okay, because I am applying the input impulse signal to the system to find out the impulse response. So when you apply the impulse signal as an input to the system at the output side, you will get an impulse response. So this is the impulse response of the system. Okay, that's why I have taken R of S is equal to 1. Have you
Yes, sir.
understood?
Got it.
Okay, so this will be the impulse response of the system. Okay. So now, if you observe this term, is this transient term or steady state term?
Transient.
Yes, impulse response always have a transient terms. Okay, now okay, so this is a C of t. Now there is a concept called steady state error. Okay, so when systems output reach at steady state, means when C of t reaches steady state at t tends to infinity. Okay, so the difference between the reference signal and the C of t gives us this steady state error. Okay, so it defines the accuracy of the system. So let us calculate the impulse. Let us calculate the steady state error for this particular impulse signal as a input. Okay. So steady state error means t tends to infinity. R of t minus C of t, where R of t is reference input and C of t is output. Okay. So what is R of t? In this case, R of t is delta of t. And what C of t you got? C of t will be 1 by tau e raised to minus t by tau u of t. Okay. So that will be del of t minus 1 by tau e raised to minus t by tau u of t. Okay. So calculate what is the steady state error you get. So what is the steady state error you get here? Okay. Now, if I draw the input, so this is the input R of t, that is equal to del of t to 0, right? Okay. So here you can see steady state error means as t tends to infinity, right? So if you observe these two signals, one is the output signal C of t and one is the input signal R of t, that is a delta of t, right? Impulse signal, impulse as the input. Now, as a t tends to infinity, as a t tends to infinity, mute your mic, okay? As a t tends to infinity, so here you can see as t tends to infinity, input is not exist, right? So input is exist at only t is equal to 0. At t is equal to 0 only input is exist. But output, okay, so input is not exist at t is equal, t tends to infinity. So for such a signal, you can't define the steady state error. So ESS can't be defined here. Steady state error can't be defined. Okay, because input doesn't exist at t is equal to infinity, because it exists at only t is equal to 0. This one, right? So this is the impulse response of the system. Now why we find out the impulse response. Now I got this impulse response of the system. So now I know what is the impulse response of the system. So if I want to calculate the unit step response, what will be the response output of my system when I apply a step signal, or when I apply a ramp signal, or when I apply the sinusoidal signal. Okay, so if I got this response, I will be able to calculate the output of this particular first order system for any input. Okay, that's why we calculate the impulse response of the system. So we will be able to calculate the uh, output of system for any input. Okay, so let us consider what will be the response of the system when we apply the unit step signal to the system. So as we know, the closed loop transfer function is this. Closed loop transfer function of the system is okay. Now we are going to apply unit step response at this input, right? So here R of t, as a R of t, at this point we will apply the unit step signal. Now R of t will be equal to U of t, that is unit step signal. And if I take a Laplace transform of it, that will be R of s. And what is the Laplace transform of unit step signal? 1 by s. Okay. So R of s is equal to 1 by s. Now if I put in this equation, if I put R of s is equal to 1 of s, so C of s will be right. So I can solve this by using a partial fraction. Okay, tau is the time constant of a system, right? As you may have studied in circuit theory, time constant of the system. Now if you do this partial fraction here, so you will get at s is equal to 0, you will get a as a 1, and b at s is equal to minus 1 by t. Right, so at that you will get minus 1. So this will be 1 upon s minus 1 upon s plus 1 by tau. Okay. So now if I take an inverse Laplace transform of this to find out the response, okay. Generally when say the response of the system, okay, so that is generally with respect to time, that is a time domain equation. Okay, so the unit step response means when you apply the unit step signal, whatever the output signal I am getting with respect to time, that is a unit step response. Okay, so that's why I am converting this particular equation in Laplace domain into time domain. So that will be C of t. So you tell me the inverse Laplace transform of this. What is it? What is the inverse Laplace transform of 1 upon s?
T.
U of t minus e raised to minus t tau upon into u of t. E raised to minus at u of t Laplace transform is what? 1 upon s plus a, right? So this is that only, na? Okay, so this is the
Yes.
okay. So this is the unit step response. So if I draw the graph here, I draw the graph here. Okay, so this is a unit step signal, input signal, and then this is e raised to minus t by tau, so that will be like so if you subtract the e raised to minus t by tau from u of t, c of t you will get as a output signal. How you will get the output signal? That will be like okay. So this will be the output signal. So here you can see how to draw this 1 minus 1 0. Okay, you just need to invert, right? Because we are subtracting this particular signal from this one, right? So this is just like an inverted signal. So this is a C of t. Okay. So so this is the unit step response of the system. Okay. So next, we need to find out what is the steady state error we get when we apply the unit step response to the system. For example, for any RC circuit, when you apply a step signal, okay? When you apply the step signal, what will be the output response you will get, okay? So there it will take some time to reach to the it takes some time to follow the input, right? Okay, to reach to the final value. So what is the final value here? Final value is 1 here, okay? So it will take some time to reach to that particular final value, right? Okay, so it depends on a time constant of a system, right? So depends on a time constant of a system, how much time it will take to reach to the final value. Okay. So let us calculate the steady state error for this particular system. What is meant by steady state error? At t tends to infinity, what is the difference between the reference input and output? Okay. So can you able to calculate the steady state error from this particular graph? So what is a steady state error? So R of this is the input graph and this is the output. So what is the steady state error here? Anyone? ठीक. So just how many of you are following this? Just raise your hand.
Sir, e to the power minus t by tau into ut.
Okay. Okay, let us see how to calculate it. So what is meant by steady state error? So here you see ESS has limit t tends to infinity. Okay, difference between the reference input and output. So what is my reference input? R of t, that is u of t. And what output I got? So what output I got here? That is here only, right? U of t minus e raised to minus t by tau u of t. So this is my output. So if I just take limit t tends to infinity, okay, so u of t minus u of t plus e raised to minus t by tau u of t, right? So this u of t will get cancelled. So when I put t is equal to infinity, when I put t is equal to infinity, what will happen? E raised to minus infinity, right? So what is the steady state error here? 0. Okay. Now from the graph, how you can determine that thing? So if you see this particular graph, okay, so this graph input is 1, okay, at t tends to infinity, what is the value of input? 1 only, right? And if you observe the output, okay, at t tends to infinity, this output will reach to its steady state. What is the steady state of this particular output? That is 1 only, right? At t tends to infinity, it will reach. Now it's increasing, right? It will take some time. If you take any system, it will take some time to reach to the steady state. Yesterday we have seen, right? We have taken the example of rising and falling edges of the clock, right? So it will take certain time to reach the steady state. So at t tends to infinity, this output signal C of t will reach to 1. And what is the difference between R of t and C of t at t tends to infinity? 1 minus 1, 0. So that's only I was asking. Okay. So like this way, the steady state error for unit step signal is 0. So what is the conclusion of this? When you apply unit step signal to the first order system, for example, if you apply the DC supply to the RC circuit, okay, so whatever the output response you will get, that will clearly follow the input. Okay, that is the conclusion here. Okay, so that particular RC circuit will clearly handle that unit step signal. That is the significance behind it. Okay, so like this way you can find out the steady state error of the system. Let us apply the next standard input signal, that is a unit ramp signal. Okay, so similar procedure. How to find out the response? You have a transfer function of your system, right? You just need to, or transfer function is what? Transfer function of the system is Laplace transform of impulse response of the system. Okay, so when you have C of s upon R of s with you, right, the transfer function. Okay, so for any input, if you want to calculate C of s, you just need to multiply transfer function with R of s, right? So what is the C of s upon R of s in our case? So this is this. Okay. Next we apply a ramp signal. We will see what will be the effect on this system output response when we apply the ramp signal. So R of t, the reference signal is ramp signal. Just a minute. Okay, so reference signal is ramp signal, that is a t into u of t. So if I take a Laplace transform of that ramp signal, what is the Laplace transform of ramp signal? That will be R of s is equal to 1 upon s square, right? So instead of R of s, I will put 1 upon s square. So that will be 1 upon tau. So that will be s square into s plus 1 by tau. So this will be the C of s. So take a partial fraction and find out the response. Okay. So right. So when I put s is equal to 0, so here will be 1, right? When I put s is equal to minus 1 by tau, so c will be equal to tau. Okay, so s is equal to 1. Right, so a is 1, right, and c is tau. So put that into this equation. Right. So just simplify this, this. So this will be like minus 1 plus tau, right? Oh, here 1, I forget to put 1 here, right? That will be 1 plus 1 by tau. All right. So that will be so b will be minus tau, right? So you got 3 values. Just put into partial fraction. Minus tau by s plus tau upon s plus by tau. Okay. So this is a C of s. So take inverse Laplace transform, right? So response is in time domain only. So what is the inverse Laplace transform of this? Tell me. C of t. What is the inverse Laplace transform of this? What?
T into U of t.
T into u of t minus tau into u of t. Tau is a constant only, no? Plus tau into e raised to minus t by tau into u of t. Right? So this is the ramp response. So can you calculate this steady state error now? Calculate the steady state error and reply in chat box. So you know the R of t and C of t. So calculate the steady state error. Okay.
Sir, is it tau?
Yes, right. So R of t is what? T into U of t minus this U of t, right? T into U of t plus tau into U of t minus tau into e raised to minus t by tau U of t. Okay, so this term will get cancelled. Then if I put t raised to infinity, this term will become 0 and what will remain? Tau only. So ESS will be tau. The steady state area will be tau. So what is the conclusion here? So when you apply any unbounded input, right? So if you see the ramp signal as a t tends to infinity, so we will see that. So if I draw the graph here, okay. So this is the input. If I say this is the input R of t, t into U of t. So output will be like this. So this will be the C of t. And if you find out the difference between these two, that will be tau. Generally what happens, practical system reach steady state at approximately 5 tau, okay? So it doesn't take infinite time, right? So practical system generally reach the steady state in 5 tau, okay? So here, okay, so I will just use a different color here. Okay, so this is the steady state error. Okay. So when you apply the ramp signal to particular first order system, you will that ramp signal will not clearly follow the output response will not clearly follow the ramp signal. Okay, so at steady state there will be a steady state error tau. Okay, this is the conclusion here. So if you talk up, we have seen 3 responses: unit ramp response, uh, unit step response, and impulse response of the system. Okay, so if you talk about the last standard test input, that is a parabolic signal. Okay, so here I can just mention, okay. So this is the thing here. Any doubt? Any doubt is there related to
No,
this?
sir.
Okay, so last standard test input you will see that is a parabolic signal. Okay, so I will just take my this will be the same. So interface fluid will be change. So here that signal will be t square by 2, right? It will be t square by 2 u of t. Laplace transform, that will be r of s. That will be 1 upon s cube, right? Okay, so c of s will be 1 by tau s cube s plus 1 by tau. Okay, so let us take a partial fraction here, s cube c by s d upon s plus 1 by tau. Okay, and then solve this. C into square into s plus 1 by tau is t into s cube. Okay, so first put s is equal to 0, so that will be 1 by tau a into 0 plus 1 by tau, so that will be 1, right? A will be 1. Then s is equal to minus 1 by tau, so that will be 1 by tau d into minus 1 by tau cube, right? So what will be the d then? Minus tau square. So now just simplify this particular expression and find out other terms. So that will be as plus a upon tau plus bs square bs by tau, so c s cube plus c square by tau. Okay, so ds cube. Now here if you see here these two are the first order terms, so okay, and if you compare these two sides, so I can write that that will be equal to 0, right? A plus b by tau will be equal to 0, and what is a? A is 1. So if I compare the first order terms, right, so that will be a is 1, no? 1 plus b by tau to 0, so b will be minus tau. Similarly, if you see, so what is remain? C is remain, no? So if you see the second order term, this, so that is also 0 only. So p plus c by tau will be equal to 0. Okay, only two terms are there. Okay. So what is a b? C will be tau square. Okay, is it right?
Yes, sir.
Okay, so just put the values in this particular equation. So if I take this equation here, okay, so this is a C of S. So 1 is 1 only, A is 1 only. A is minus tau upon S square. C is tau square upon S plus D is what? Minus tau square. Okay, it will be minus tau square upon S plus 1 by tau. Okay, so let us take a IRT of this inverse Laplace transform. So now you tell me what is the C of t. C of t will be, this is 1 upon s cube, right? So parabolic, t square by 2 into u of t. So this is a ramp. So minus tau t into u of t plus this is unit step. Tau square into u of t minus tau square into e raised to minus t by tau into u of t. Okay, have you understood this inverse Laplace transform of each term? We have taken the Laplace transform, right?
Yes, sir.
So this is the parabolic response for the first order term. Sorry, for the first order system when you apply the parabolic signal. Unit parabolic. Okay. So you got this. Now you just find out the steady state error. So what is the steady state error? Steady state error will be limit t tends to infinity r of t minus c of t. So r of t is t square by 2 into u of t and c of t is this one. So just take a difference. Okay. So t square by 2 into u of t minus this term. Okay, so this will be get cancelled. These two terms will be get cancelled. So what is a steady state error now? If you put t is equal to infinity in this equation, so this term will become 0, right? E raised to minus infinity, 0. In this term there is a no t term. So here t term is there. So what will be the steady state error? Anyone can reply. What will be the steady state error?
Tau minus tau square.
No. When we put t is equal to infinity, na?
0.
Or infinity, na? So this will be, t will be infinity. Here t is there, na? So this term will become infinity. Here no t term is there.
Yes, yes.
And this will be 0. So steady state error will be infinity. So what is mean by this? So for the first order system, when we have applied the unit step signal, okay, that standard signal, output response will be clearly following the input, okay. So next we have applied the unit ramp signal to first order system, okay. So if you apply the unit ramp signal at t tends to infinity, we got a steady state error tau, okay. But when you apply a parabolic signal, okay, when you apply the parabolic signal, so we got an infinite error when you apply. So when you apply this parabolic signal to this particular RC filter, so that output response, at the output response we will get infinite error, okay. So such a kind of signal you can't apply, the parabolic kind of signal you can't apply to first order system, because you will get steady state, infinite steady state error, okay, because that particular system will not clearly follow the input. So this is the main conclusion here between these